Hello there, and welcome to the Sleepy Space Channel. Tonight, the strange and quietly unsettling truth that every textbook picture you have ever seen of our solar system is wrong. The flat disk, the 8 planets in a neat line, the orderly diagram with the sun at the center, none of that is what the solar system actually looks like. The real shape is something stranger. A sphere, mostly dark, mostly invisible, surrounded by structures no eye has ever seen. And from far enough away, almost nothing about our solar system can be seen at all. Tonight, we will leave Earth, slowly, and look back at our own home from a great distance and see what is actually there. If you find these slow explorations worth your time, a like or a subscribe helps the channel reach others who might enjoy them too. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The diagram and the real shape. Every textbook image of our solar system shows the same picture. A flat disk. 8 planets spaced along a single plane. The sun at the center. Everything moving along clean ellipses, arranged neatly, as if the universe itself had been drawn by a careful hand on a sheet of paper. It is a useful diagram. It is not what the solar system actually looks like. The diagram is a tool. It shows the parts that catch light, in the order they were taught to schoolchildren a long time ago. The real solar system is something stranger, something quieter, something almost entirely invisible. The diagram is a flat plate. The real solar system is a sphere, and the sphere is mostly dark. There is something quietly sobering about the gap between the picture and the place. The picture is a small, bright, orderly arrangement. The place is enormous, mostly empty, and almost completely invisible from any meaningful distance. The diagram suggests a tidy little system that you could hold in your hand. The reality is a vast and unsettling sphere that we sit at the very center of, and that we cannot, from inside it, see clearly. Almost everything that makes our solar system what it is hidden from us by sheer distance and sheer darkness. The first thing worth understanding is that the planets are only the innermost detail of a much larger structure. Around the planets lies a thin disk of icy debris called the Kuiper Belt, extending out to about 50 astronomical units. Beyond that lies a vast magnetic bubble inflated by the sun's wind, shaped not like a sphere, but like a long teardrop drawn out by the solar system's motion through the galaxy. This is the heliosphere. Beyond the heliosphere lies a still vaster shell of frozen objects, spread in every direction, extending nearly a full light-year from the sun. This is the Oort cloud. And beyond the Oort cloud, the sun's gravitational reach finally fades into the gravitational pull of the rest of the galaxy. The diagram shows a plate. The real solar system is a sphere. A diffuse, mostly invisible sphere, with one bright point of light at its center and a thin lacework of orbits buried in its innermost interior. From the outside, almost none of it can be seen. From the outside, we are simply a star, one star among many, with a faint, slowly expanding sphere of radio noise spreading out around us at the speed of light. That is what tonight is about. We are going to leave Earth, slowly, by degrees, and look back at our own solar system from progressively farther away. We will pass the outer planets. We will cross the boundary of the sun's wind. We will drift through the Oort cloud. We will continue outward until our entire solar system has become a faint yellow point, indistinguishable from thousands of other stars. And then we will ask the only question worth asking from there. What does our solar system look like from here? What does it tell anyone who happens to be watching about the place where you are listening from now? Settle in. None of this is urgent. The solar system has been doing what it does for 4.5 billion years. It is not going anywhere. You are not going anywhere. We are simply going to spend the next while looking at it from outside, slowly, and from quite a long way away. There is something worth saying clearly about the gap between maps and places. A map is a tool for finding things. A place is a tool for being in. The two are related, but not the same. The diagram of the solar system is a map. It shows you where to look, in what order, with what relative spacing. The actual solar system is a place three-dimensional, dark in most directions, layered, mostly invisible, mostly empty. The map is small enough to fit on a page. The place is large enough that no photograph has ever captured it as a whole. None ever will. There is no vantage point in the universe from which our solar system can be seen entire, in a single image, with all of its parts at once. Even the most distant probes we have sent have looked back at home and seen only the sun and a few of the nearer planets, scattered across an image like dust motes in a beam of light. The very idea of looking at the solar system from outside is, in some quiet sense, an act of imagination. No one has done it. No one will do it for a long time. But the question is worth asking, because the answer changes how the inside view feels. From inside, the planets seem central. From outside, they are not. From inside, the sun seems vast. From outside, it is not. From inside, the solar system feels like the whole world. From outside, it is one entry in a very long list. It is worth saying that the diagram has its purposes. It is how children first learn the names of the planets. It is how mission planners draw orbital trajectories. It is how astronomers visualize gravitational dynamics. The diagram is correct in its own way. It captures the orderly orbital mechanics of the planets quite faithfully. It just is not the whole picture. The whole picture is a sphere, and the diagram is the central thin slice of that sphere, and the slice has been drawn on flat paper, because flat paper is what we had to draw on. So as we begin the outward journey tonight, set the diagram aside. Hold instead the idea of a sphere with a bright point at the center. A sphere mostly filled with dark, cold, slow material. A sphere that, from inside, feels like home. A sphere that, from outside, looks like one small star. Part 2. Outward through the plane. We begin by leaving the inner solar system. The 4 rocky planets, Mercury, Venus, Earth, and Mars, are crowded into the innermost portion of the Sun's gravitational reach. Mercury orbits at about 4/10 of an astronomical unit, where an astronomical unit is the average distance between Earth and the Sun. Venus orbits at about 7/10, Earth at 1, Mars at about 1.5. Beyond Mars lies the main asteroid belt, a thin scattering of rocky bodies between Mars and Jupiter. And beyond the asteroid belt lie the 4 giant planets. Jupiter orbits at about 5 astronomical units, Saturn at about 10, Uranus at about 19. Neptune, the outermost planet, orbits at about 30 astronomical units, which is roughly 2.75 billion miles from the Sun. The light that left the Sun reaches Neptune in about 4 hours. From an observer at Neptune's distance, the Sun is still by far the brightest object in the sky, but it is no longer a wide disk. It is becoming a single, fierce, brilliant point of light. Now imagine that we are moving outward. We do not need a specific speed for this. We simply need to move. As we accelerate away from the sun, the planets begin to shrink. From any reasonable interstellar fraction of light speed, the planets pass behind us within minutes. Neptune itself would shrink to a pale blue dot. And then it would be gone. Past Neptune, the solar system does not end. It thins. The region from about 30 to 50 astronomical units is occupied by the Kuiper belt. This is the second of the solar system's two main reservoirs of leftover construction material, the asteroid belt being the first, much smaller, much closer in. The Kuiper belt is wider and contains more total mass than the asteroid belt, but it is spread over an enormously larger volume. Pluto is one of the largest known members of the Kuiper belt, but it is not unique. There are likely hundreds of thousands of bodies in the belt, larger than about 60 miles across. Some are spherical enough to qualify as dwarf planets, Eris, Makemake, Haumea, and others. Some are on stranger, more extended orbits. Sedna swings outward to perhaps 1,000 astronomical units before slowly returning. Most are smaller, dimmer, and uncatalogued. Crossing the Kuiper belt would not look the way Hollywood asteroid fields look. The belt is vast enough and its members are sparse enough that any straight line through it would, in practice, miss every single object. Travelers would see a sparse scattering of icy bodies in the distance and otherwise mostly empty space. The Kuiper belt is a region whose primary characteristic is emptiness. Space does not begin at Neptune. It simply gets progressively emptier the further out one goes. And as we move through the Kuiper belt, the light from the sun changes. Sunlight weakens with the square of the distance from the source. At Neptune, sunlight is about 1,000 times fainter than at Earth. At 50 astronomical units, near the outer edge of the Kuiper belt, it is roughly 2,500 times fainter than at Earth. The sun, still the brightest object in the sky by an enormous margin, is no longer a disk one needs to glance away from. It is a fierce, brilliant point of light. You could look at it without flinching. The planets are no longer visible to the naked eye. The lacework of orbits has disappeared into the glare of a single distant star. This is the first quiet realization of the journey. From only 50 astronomical units away, the solar system has already begun to look like nothing more than a bright star surrounded by darkness. The planets are gone. The disk is invisible. What you see is a single star and the dark, and that is most of what anyone watching from any meaningful distance will ever see. The planets, while we are talking about them, deserve a moment of attention in their own right. We will not see most of them again for the rest of this video. Once we are far enough out, they disappear. So while they are still visible, here is what they look like, briefly. Mercury is small, grey, and cratered. It has almost no atmosphere. Its days are blazing hot, and its nights are bitterly cold, with a temperature swing of nearly 1,000 degrees between sunlight and shadow. It orbits the sun once every 88 Earth days, faster than any other planet. From any distance beyond a few astronomical units, Mercury is functionally invisible. It is too small and too close to the sun's glare. Venus is similar in size to Earth, but completely different in character. Its surface is hidden under a thick atmosphere of carbon dioxide, with clouds of sulfuric acid, and surface temperatures hot enough to melt lead. Venus is brighter than any other planet in Earth's night sky, but from outside the inner solar system, it too disappears into the glare of the sun. Earth is the third planet. From space, It is blue and white and brown, with thin clouds, large oceans, and the only known biosphere in the universe. Earth is the only place we know with certainty that life exists. It is also, from any meaningful interstellar distance, a faint dot. Mars is small, cold, and reddish. It has a thin atmosphere, 2 small moons, and the largest volcano in the solar system. Mars is the planet most often considered as a candidate for human exploration, although its hostility to human survival is considerable. Then comes the asteroid belt, and beyond it the giant planets Jupiter, the largest, with its great red spot and its dozens of moons. Saturn, the second largest, with its enormous and elegant ring system. Uranus, tilted nearly sideways on its axis, with a small set of dark rings. And Neptune, the farthest, blue and stormy and quietly violent in the upper atmosphere. These are the 8 planets. They are the parts that catch light and that we have given names to and that we draw in the diagrams. From the outside view we are building tonight, they are also the parts that disappear first. As we accelerate outward, the planets shrink. Mars goes first. Then Jupiter and Saturn fade. Then Uranus and Neptune. Then nothing of them is visible at all. Only the Sun remains. And then, eventually, even the Sun begins to look like a star. The light that leaves the Sun moves at about 186,000 miles per second. At that speed, it takes light 8 minutes to reach Earth, 43 minutes to reach Jupiter, and roughly 4 hours to reach Neptune. That is the scale of the planetary system, measured in the time it takes light to cross it. It is small compared to the scales we will soon be using. From the outer Oort cloud, light from the Sun takes 1.5 years to reach a passing object. From the nearest star, the Sun's light takes 4 years to arrive. From the edge of the radio bubble, the Sun's light has taken a century to arrive. The numbers grow and grow and grow. Part 3. The heliosphere. We have left the planets behind. We have moved through the Kuiper belt and out beyond its sparse outer edge. The Sun is now a brilliant point of light far behind us. To the eye, very little has changed. But physically, the space we are moving through is not the same as the space we left. The Sun does not merely shine. It exhales. Continuously, in every direction, the Sun releases a stream of charged particles, protons, electrons, and a smaller fraction of heavier ions that travels outward at speeds of several hundred miles per second. This is the solar wind. The solar wind fills the region around the Sun for an enormous distance, far beyond the orbits of the planets. The volume of space that the solar wind dominates is called the heliosphere. For most of human history, the solar wind was invisible. It does not glow. It does not press against anything we can see. It was only with the first spacecraft to leave the Earth's vicinity that we began to measure it directly. And only with those measurements did we begin to understand the true shape of the region of space that we live inside. If the Sun were standing still in the galaxy, the heliosphere would be roughly spherical. The solar wind would push outward equally in every direction until the pressure of the gas between the stars eventually stopped it. That gas, called the interstellar medium, is enormously thinner than anything found on Earth, but on the scale of the solar system, it is not nothing. It pushes back. The Sun is not standing still. The solar system as a whole is moving through the local interstellar medium at roughly 43,000 miles per hour. That motion compresses the solar wind on the leading side and stretches it out on the trailing side. The bubble is not a sphere. The bubble is shaped like a teardrop, or like a long comet, or, in some recent models, like a flattened croissant. On the leading side, the heliosphere has a blunt, rounded forward face. On the trailing side, the solar wind streams out into a long, drawn-out tail that may extend several hundred astronomical units behind us. Astronomers call this trailing region the heliotail. A ship moving through water pushes a small wave ahead of it and leaves a long wake trailing behind. The heliosphere is the solar system doing the same thing, on a scale that dwarfs the planetary orbits several times over. The planets, with their tidy ellipses, are buried near the center of the bubble. The bubble itself extends far beyond them, drawn into its asymmetric shape by motion through a medium that is too thin for us to see, but not too thin to push. The boundary of the heliosphere is not a single sharp wall. It has a layered structure. Working outward from the Sun, the relevant zones go in roughly this order. First comes the termination shock. This is the region where the supersonic solar wind suddenly slows as it begins to feel the resistance of the interstellar gas. The termination shock lies somewhere around 80 to 100 astronomical units from the Sun. Beyond the termination shock lies the heliosheath, a thick, turbulent region where the slowed and heated solar wind piles up before flowing outward toward the tail. Beyond the heliosheath lies the heliopause, the true outer boundary, the place where the pressure of the solar wind exactly matches the pressure of the interstellar medium. Inside the heliopause, particles from our Sun dominate. Outside, the galaxy's particles take over. The heliopause sits at roughly 120 astronomical units from the Sun on the leading side, and is presumably much farther out along the trailing tail. There is one more feature worth mentioning, although it remains debated. On the leading face, where the heliosphere meets the incoming interstellar medium head-on, there may be a soft bow region, a gentle bow wave, where the interstellar gas is slowed and warmed as it encounters the bubble. Older models referred to this as a true bow shock, analogous to the bow shocks observed around other stars. More recent measurements suggest that, for our particular star, the structure is gentler closer to a bow wave than a bow shock. Either way, this would be the first physical boundary an inbound traveler from the leading direction would encounter. Not a wall of light. A wall of physics. 2 human-built spacecraft have actually crossed the heliopause. The first crossed in the early 2010s. The second crossed several years later, in 2018. Both are still transmitting at the time of this writing. Both are now drifting outward through interstellar space at a tiny but steady speed, far too slow to reach any nearby star in any reasonable timescale, but fast enough that every year places them a little further beyond the boundary. On the inward side of each crossing, the instruments saw a particle environment dominated by ions of solar origin. On the outward side, they saw a sudden and steep increase in galactic cosmic rays and a sharp drop in solar particles. The boundary was not visible to any optical instrument on board, but it was unmistakable in the data. 2 spacecraft, decades after launch, finally confirmed by direct measurement what theory had long predicted, that there is a real, physical edge to the region of space dominated by the Sun. We have crossed that edge in our imagined outward journey. The solar wind is now behind us. But the solar system is not behind us yet. Not even close. The solar wind is worth understanding a little more closely, because its behavior is what gives the heliosphere its character. The Sun's outer atmosphere, the corona, is enormously hot. Its temperatures reach into the millions of degrees, far hotter than the surface of the Sun itself. The mechanism by which the corona is heated to such extreme temperatures is one of the long-standing open questions in solar physics. Whatever the mechanism, the consequence is that the corona is so hot that it cannot be contained by the sun's gravity. The outermost layers of the corona are continuously being released into space, in a steady stream of charged particles, moving at speeds that range from roughly 250 miles per second to nearly 500 miles per second. The slower component of the solar wind comes from the equatorial regions of the sun, from a structure called the streamer belt. The faster component comes from the polar regions, from coronal holes open regions of the sun's magnetic field, where the solar wind escapes more freely. The mix of fast and slow wind creates a complex three-dimensional structure of flow throughout the inner solar system. Embedded in the solar wind is the sun's magnetic field. As the sun rotates, its magnetic field is dragged outward by the wind, forming a vast, spiraling pattern called the Parker spiral. The field lines do not extend straight outward, they curl, like the streams of water from a rotating sprinkler. This spiraled field threads the entire heliosphere and influences the motion of every charged particle within it. The heliosphere is, in effect, the sun's magnetic territory. Inside it, the sun's magnetic field dominates. Outside it, the interstellar magnetic field dominates. The two fields meet at the heliopause, and they do not align. The orientation of the magnetic field jumps when one crosses the heliopause. This was one of the most striking direct measurements made by the two spacecraft that have crossed it. They detected the change in magnetic field orientation as one of the clearest signals that they had, in fact, entered interstellar space. Galactic cosmic rays are an important part of the picture. These are high-energy particles, mostly atomic nuclei, that come from elsewhere in the galaxy, from distant supernovae, from active galactic nuclei, from sources we do not yet fully understand. They are charged, and they are fast. When they encounter the heliosphere from outside, most of them are deflected, slowed, or excluded by the sun's magnetic field. The heliosphere acts as a kind of soft shield, lowering the galactic cosmic ray flux at Earth by a substantial fraction compared to what it would be in interstellar space. We are, in this respect, sheltered by our star not just from cold and dark, but from the high-energy particles that fill the rest of the galaxy. When the two spacecraft crossed the heliopause, one of the things they registered was the increase in galactic cosmic rays, an increase of about a third over what they had measured inside the heliosphere. That increase is the difference between the inside of the bubble and the outside. It is the measurable expression of the shielding that the sun provides. The heliosphere is, in other words, not just a region of space. It is an environment. It is a slightly different physical regime, with its own particle population, its own magnetic field structure, and its own cosmic ray flux. We have lived inside it for the entire history of life on Earth. We did not know it was there until our instruments became sensitive enough to measure its boundary, and we did not know its full shape until our spacecraft began to cross it. The sun has been holding this bubble around us for 4.5 billion years. We have only known about it for a few decades. It is worth pausing on one more thing about the heliopause crossing. The first probe crossed it in late 2012, after 35 years of travel from Earth. The second crossed in 2018, after 41 years. By the time the second crossing happened, the engineers who had originally designed the spacecraft were largely retired. The instruments still worked. The radio transmitters still worked. The plutonium that had powered them for 4 decades was still producing usable amounts of heat, although less than it had at launch. The spacecraft were drifting outward at about 38,000 miles per hour, which by any human standard is fast, and by the standard of interstellar distances is barely a crawl. Even at that speed, neither probe will reach the inner edge of the Oort cloud for roughly 300 years. Neither will reach the outer edge for tens of thousands of years. Neither will pass within a few light years of another star for many tens of thousands of years. The two probes are, in a sense, the first ambassadors of the inner solar system to interstellar space. They are not fast enough to matter on any short timescale, but they are out there. They will continue drifting onward long after the first civilization that built them has forgotten what they were. They are simple. They are stubborn. They are the first physical artifacts of human technology to leave the bubble we have lived inside for the entire history of our species. Part 4. The Oort cloud. Beyond the heliopause, the sun's wind no longer reaches us, but the sun's gravity still does. The sun's gravitational reach extends far beyond the heliosphere, perhaps 1,500 to 2,000 times farther. And inside that gravitational reach lies the largest and least seen component of the solar system, the Oort cloud. The Oort cloud begins at about 2,000 astronomical units from the sun. Its outer edge is harder to pin down, but it likely extends to about 100,000 astronomical units, which is roughly 1 6/10 light years. That outer edge is about a quarter of the way to the nearest star. The Oort cloud is not a small structure. By volume, it is the solar system. The planets, the asteroid belt, the Kuiper belt, and the heliosphere together occupy only a tiny inner bright knot of what we usually mean when we say solar system. The Oort cloud holds almost all the rest. The Oort cloud is not a disk. It is a sphere, a roughly three-dimensional shell that surrounds the solar system in every direction at once, above the plane of the planets, below the plane of the planets, and out to the sides. Imagine a soft, frozen sphere centered on the sun, with a roughly hollow interior and a thick, spherical outer shell. The planets sit inside the hollow interior. The Oort cloud is the shell. Astronomers sometimes divide the Oort cloud informally into two regions. The inner Oort cloud, sometimes called the Hills cloud, extends from roughly 2,000 to perhaps 20,000 astronomical units. It is shaped more like a thick donut, somewhat aligned with the plane of the planets. The outer Oort cloud extends from 20,000 astronomical units outward, and it is much more spherical. Most of the cloud's interesting visitors to the inner solar system come from the outer spherical portion. The Oort cloud holds an estimated 1 to 2 trillion objects. These are small icy bodies, kilometers across at most. Frozen water, frozen methane, frozen carbon monoxide, frozen ammonia, and organic ices darker than coal. They are leftover construction materials from the formation of the planets. 4.5 billion years ago, when the solar system was forming, the young giant planets gravitationally scattered enormous numbers of icy planetesimals outward. Most of those scattered objects were ejected entirely. A small but enormous fraction were parked, gently and slowly, in distant orbits around the sun. Those distant orbits are the Oort cloud. These orbits are slow. The planets, by comparison, are racing. Mercury completes one orbit around the sun every 88 Earth days. Earth completes one in a year. Neptune takes about 165 years. An Oort cloud object can take tens of thousands of years to complete a single orbit. The outermost Oort objects take many millions of years. They move so slowly, on orbits so enormous, that from our perspective inside the planetary system they appear functionally motionless. They simply hang there in the dark, far from the warmth of the sun, drifting on tracks too vast to perceive. No telescope has ever directly imaged an Oort cloud object in situ. The objects are small. They reflect almost none of the already faint sunlight that reaches them, and they are immensely separated from one another. The average spacing between Oort cloud objects is comparable to the spacing between stars in the solar neighborhood. The cloud is dense in total mass, but vanishingly thin in any local sense. All current instruments are blind to it at those distances. We know the Oort cloud is there because of the comets. Every few years, the inner solar system is visited by a long-period comet, a comet whose orbit takes thousands or millions of years to complete. The orbits of long-period comets are not aligned with the plane of the planets. They arrive from every direction in the sky: above the plane, below the plane, out to the sides. The distribution of incoming trajectories is spherically symmetric. That spherical symmetry is the Oort cloud's signature. It tells us that the reservoir these comets come from must itself be spherical, surrounding the solar system in every direction at once. The cloud is not still. Slowly, gently, the gravitational nudges of nearby stars passing by over millions of years stir its outer regions. The gentle differential pull of the galaxy itself, the galactic tide, pulls at the outermost members. Occasionally, very rarely, a passing star or a gravitational tug from the galaxy is enough to send one Oort object inward. The object then falls. It falls for thousands of years, then for tens of thousands of years, then for hundreds of thousands of years, slowly accelerating as it nears the center of the sun's gravitational well. Eventually, it arrives. As it nears the sun for the first time in its multi-billion-year history, the surface ices begin to warm. The object grows a coma of evaporating gas. A long, bright tail develops, streaming away from the sun, and the object, now visible to telescopes and sometimes to the naked eye, becomes what we recognize as a comet. Most of these long-period visitors will round the sun once, then climb back out, returning to the cloud on slow orbits that may not bring them back for 100,000 years. A small fraction will be perturbed onto trajectories that eject them entirely from the solar system. A few may collide with the inner planets. But the vast majority simply make a single bright pass and disappear back into the dark, going back to wait among the trillion other frozen bodies that surround us. This is the soft, important fact about the Oort cloud. The cloud is invisible to anyone watching from outside the solar system. But every now and again, when one of its members falls inward, it briefly catches fire in the sunlight, and the cloud announces itself by sending a single bright flare into the inner planetary system. That flare is, in a sense, the only visible expression of nearly the entire mass of the outer solar system. Most of what makes our solar system feel large, from a galactic perspective, is dark, cold, slow, and silent. Once in a long while, a piece of it falls inward and briefly burns. The mechanics of how an Oort cloud comet finds its way to the inner solar system are quietly remarkable and worth a slow pass. The cloud's outer regions are sensitive to gravitational influences that, at smaller distances, would be entirely negligible. Three influences in particular shape the behavior of the cloud over long timescales. The first is the galactic tide. The galaxy as a whole has a gravitational field that varies slightly with position. The sun feels the average pull of the galaxy on one side and the average pull of the galaxy on the other side, and the very small difference between those two pulls is what we call the galactic tide. Inside the planetary system, The tide is utterly negligible. The sun's pull dominates by a factor of millions. But at the outer reaches of the Oort cloud, where the sun's pull is weak, the tide becomes important. It slowly perturbs the orbits of the cloud's outer members, sometimes nudging them into orbits that bring them closer to the sun on each pass. The second is the passage of nearby stars. The sun, like every star in the galaxy, moves through the local stellar neighborhood. Other stars pass by at distances of a few light years, over timescales of millions of years. Sometimes rarely, but inevitably a star passes much closer. When that happens, its gravitational influence stirs the outer Oort cloud, perturbing the orbits of some of its members. A star passing within a light year of the sun would send a shower of comets falling inward over the following hundreds of thousands to millions of years. The third is the passage of molecular clouds. The galaxy contains large, dense clouds of cold gas and dust, scattered through the spiral arms. Most are far away, but the sun occasionally moves through one. When it does, the cloud's gravitational pull on the outer Oort can be strong enough to disturb the cloud's stability for a long time afterward. Over the 4.5 billion years of the solar system's history, these three influences have stirred the outer Oort cloud many times. Most of its original members have been ejected entirely, flung out of the solar system on hyperbolic trajectories, never to return. A smaller fraction remain in slow, almost stable orbits, occasionally perturbed inward to make a single bright pass. When one of these objects finally arrives in the inner solar system, the journey it has just completed is staggering. The object began at, say, 50,000 astronomical units from the sun. It fell for tens of thousands, perhaps hundreds of thousands of years. It accelerated slowly as the sun's gravity became gradually stronger. By the time it reached the inner planets, it was moving at speeds of tens of miles per second. It rounded the sun in a few weeks or months. Its surface ices, never previously warmed in any meaningful way, began to sublime to turn directly from solid into gas, releasing a coma of dust and gas around the nucleus. The solar wind and the pressure of sunlight pushed that coma outward, away from the sun, into the long tails we see streaming behind comets in the night sky. Then, as the comet pulled away from the sun on its outward leg, the heating diminished. The coma faded. The tail faded. The object continued outward, no longer visible, on a trajectory that would carry it back into the cloud, or, occasionally, on a hyperbolic trajectory that would carry it out of the solar system entirely. Some long-period comets are not single passes. Some return on orbits of a few hundred years to a few thousand years, having been perturbed onto more bound orbits during their first inner solar system encounter. These are the slightly shorter period comets that astronomers can predict and re-observe. Many of the very long period ones, by contrast, will not return for 100,000 years or more, long after every astronomer alive today has been forgotten, long after the civilization that first photographed them has been replaced. The Oort cloud, in this sense, is not a static structure. It is a slowly churning reservoir. Most of its members are still where they have been for billions of years. A few are slowly nudged inward by the gentle influences of the galaxy and the passing stars. A still smaller few make the long journey inward, briefly catch fire, and either return to the cloud or are ejected. From outside the solar system, none of this is visible. From inside, every long-period comet is a single, quiet messenger from the outermost reaches of where we are. A small detail about the cloud, easy to miss. The Oort cloud's outermost members are loosely enough bound to the sun that they could, in principle, be exchanged with the Oort clouds of nearby stars. When the sun was very young, it formed within a dense cluster of other young stars. The cluster has long since dispersed, but during the period of its existence, the gravitational fields of the cluster's members would have repeatedly perturbed each other's outer Oort clouds. It is possible, even likely, that a small fraction of the icy objects in our own outer Oort cloud did not originate with the Sun at all. They may have been captured from a sibling star in the birth cluster, drifting outward with their original star for a time, then transferred to the Sun's gravitational influence by a close encounter during the cluster's last days together. Conversely, some of the icy objects that originally formed with the Sun may now reside in the Oort clouds of other stars, scattered across the galaxy by the same exchanges. This is a quiet thing. It means that the Oort cloud is not, strictly speaking, entirely ours. Some of its members are from elsewhere. Some of our original members are now elsewhere. The cloud is a record not only of the formation of our own solar system, but of the larger neighborhood in which we were born. The frozen objects out there carry, in their compositions and orbits, traces of a stellar nursery that dispersed billions of years ago and that no longer exists in any recognizable form. The Oort cloud is, in this sense, the oldest neighborhood we still have. We have not lost it. We are still living in part of it. Part 5. The gravitational edge. The outer edge of the Oort cloud is also the gravitational edge of the solar system. Beyond about 1.5 to 2 light-years from the Sun, the gravitational pull of nearby stars begins to outweigh the gravitational pull of the Sun. Inside that radius, an object is bound to the Sun. Outside, an object belongs to the galaxy. The volume within which the Sun is the dominant gravitational influence is sometimes called the Sun's Hill sphere. The Hill sphere is the soft outer boundary of the solar system. It is not a wall. It is a fade. The Sun's gravitational influence does not stop. It simply becomes weaker than the combined gravitational influence of every other star, every cloud of gas, and every massive structure in the galaxy. The nearest star system, called Alpha Centauri, sits well outside the Sun's Hill sphere. Alpha Centauri is actually 3 stars, gravitationally bound to one another. 2 of them, Alpha Centauri A and Alpha Centauri B, orbit each other closely, forming a binary at the heart of the system. The third, a small, dim red dwarf called Proxima Centauri, orbits the inner binary much farther out. The whole system lies a little over 4 light-years from the Sun. Alpha Centauri A is slightly brighter than our Sun, slightly larger and slightly hotter. Alpha Centauri B is slightly smaller and dimmer. Proxima Centauri is far smaller and far dimmer than either, and is actually the closest individual star to the Sun at about 4.25 light-years. In the broadest possible reading, the outer Oort cloud of our Sun and the outer Oort cloud of Alpha Centauri may even overlap. The 2 stars may share, in some quiet sense, a borderland of frozen objects. The solar system does not so much end as fade into the next. The galaxy has no walls between its solar systems, only soft gradients of influence. This is one of the gentler implications of the outside view. We sometimes imagine the solar system as a tidy little region of space with a clear boundary, surrounded by an even tidier wilderness of interstellar nothing. The reality is gentler. Our solar system is a soft swelling of gravitational and material structure in a galaxy that is filled with similar soft swellings. There is no hard wall. There is only the slow fade of one star's influence into the influence of the next. The idea that the solar system fades rather than ends is worth holding for a moment. We are so accustomed to walls and edges and gates in our ordinary lives that the gradient nature of the solar system's boundary can feel strange when one first encounters it. There is no wall at the outer Oort cloud. There is no signpost. There is no transition zone marked in any visible way. There is only the slow dilution of the Sun's gravitational influence and the slow dilution of the Sun's leftover material. By the time one reaches the outer Oort cloud, the Sun's pull is so weak that it can be overruled by the gentle pull of nearby stars and the gentle pull of the galaxy itself. A passing star tugs at the Oort objects, and they shift. The galactic tide pulls at them, and they shift further. The boundary, such as it is the line beyond which the shifting becomes more important than the binding. That line is not sharp. It moves over time. It moves with the direction one is traveling, since the Sun's gravitational influence is somewhat asymmetric. It moves with the local stellar neighborhood, since the gravitational backdrop varies as nearby stars come and go over millions of years. In a very real sense, the question of where the solar system ends does not have a single answer. It has several, depending on what one chooses to measure. The heliopause ends at about 120 astronomical units on a leading face direction, and that is where the Sun's particles stop dominating. The Sun's gravitational dominance ends at about 1.5 to 2 light-years, which is far farther out. The Sun's chemical dominance, the region containing material that originated with the formation of the solar system, as opposed to material that originated with other stars, fades over a similar range. None of these boundaries coincide. None of them are walls. All of them are fades. This is gentler than the textbook picture. The textbook picture suggests a definite, identifiable end. The reality is more diffuse. We live inside a soft swelling of material and influence in a galaxy that is full of similar swellings. The galaxy is not divided into compartments. The galaxy is a slow gradient. It is worth noting that this is not a new observation. It is something astronomers have known for a long time. But the public picture of the solar system, the one that lives in classrooms and on the covers of textbooks, has not quite caught up. We still talk about the solar system as if it had a clear end. From the outside, it does not. Nor does it have a clear beginning in the directional sense. As we move inward from outside, there is no signpost saying we have entered the solar system. There is only the gradual increase in cometary debris, the gradual increase in solar wind particle density, the gradual increase in the apparent brightness of the central star. The change is real, but it is gradual. The solar system is not a place one enters with a definite step. It is a place one approaches. This is, in some way, easier to believe of large things in general. Cities fade out at their edges. Forests fade out at their edges. Oceans, technically, do not. But almost everything else of any size, when one looks closely, fades. The solar system is no different. It is, in this respect, like every other large thing in nature. Part 6. The view from a few hundred astronomical units. Let us pause now at 500 astronomical units from the Sun. We are well beyond the heliopause. We are still inside the Oort cloud, in a region no human-built spacecraft has yet reached. And we will simply look around. The Sun is still by far the brightest object in the sky. From 500 astronomical units, sunlight is about 10,000 times fainter than it is at Earth. That sounds like a great deal of dimming. It is. And yet the Sun, from this distance, is still hundreds of times brighter than any other star around it. It is a fierce, brilliant point of light. Looking at it, would not hurt. There is no disk to it anymore. Even the largest telescopes here would resolve only a tiny, dazzling speck where, from Earth, we would have seen a wide, round face. None of the planets are visible to the naked eye. Jupiter, the largest, would be hopelessly lost in the sun's glare. Saturn, with its enormous rings, would be invisible without sophisticated optical equipment. The smaller planets would not even be candidates. The entire orderly diagram we drew for ourselves on paper is gone. We have arrived at the first distance at which the solar system, from outside, simply does not look like its diagram. It looks like a single bright star. The heliosphere is invisible. The boundary that our spacecraft instruments crossed and that they registered as a sharp threshold in particle counts and magnetic field orientation gives off no light. To an instrument tuned to charged particles or cosmic rays, the boundary is unmistakable. To an eye, it is nothing. The Oort cloud is invisible. Its individual objects are too small, too dim, and too sparsely distributed to register on any imaginable visual instrument. We are inside the cloud now, and we cannot see it. We can only know it is there by inference and by the occasional comet falling inward toward the distant star at the center. The galaxy itself, however, is on full display. The Milky Way's band would be sharper here than on any moonless mountain night on Earth. There is no atmosphere to dim it, no city lights to wash it out. The familiar constellations of Earth's night sky would still be recognizable, almost unchanged, because the nearest stars are far enough away that a few hundred astronomical units of sideways motion barely shifts their apparent positions. The night sky, from 500 astronomical units, looks almost exactly like the night sky from Earth, except for one detail. The sun has become one of the stars. This is the first place from which our home star, the sun, looks like a star. From inside the planetary system, the sun is the daytime. From here, the sun is one of the nighttime points. A bright one, the brightest, but still a point. From here, our solar system is one bright yellow star, surrounded by a vast invisible bubble of charged particles shaped like a teardrop, surrounded by a vast invisible sphere of frozen objects extending out to nearly a light year in every direction. None of those last two structures can be seen. There is only the star and the dark and the long pale band of the galaxy beyond. The night sky from 500 astronomical units is worth describing more carefully because it is one of the easier to imagine perspectives from anywhere outside the planetary system. The familiar constellations of Earth's night sky would still be recognizable, almost unchanged. Orion would still be Orion. Cassiopeia would still be Cassiopeia. The Big Dipper would still be the Big Dipper. The constellations are made of stars at distances of dozens to hundreds of light years from Earth, and 500 astronomical units of sideways motion barely shifts their apparent positions at all. The stars would still occupy almost the same positions in the sky. There would, however, be one new bright point that any observer would notice. Where the sun used to be the daytime, there is now a single, fierce, brilliant star. Whichever direction the observer has moved away from the sun appears at the corresponding place in the sky. It is brighter than any other star around it by a substantial margin. It does not, however, dominate the sky the way it used to. The sky is now mostly dark, with one bright point at one position and many dimmer points at other positions. The color of the sky is true black. There is no atmosphere here. There is no scattering. There is no twilight. There is no moonlight. since the moon is hopelessly lost in the sun's glare. There is no zodiacal light, since we are now well above the densest interplanetary dust. There is only the dark and the stars, and one fierce point that used to be home. The pale band of the Milky Way runs across the sky just as it does from Earth, but more sharply. Without atmospheric scattering, the band is crisper. The dark dust lanes within it are easier to see. The galactic center is a faint glow toward one direction. Individual bright stars stand out more clearly. The galaxy is more obviously a galaxy from out here than it is from inside an atmosphere. There is one more detail worth noting. From 500 astronomical units, the parallax of nearby stars is large enough to be noticeable in repeated observations. If our hypothetical observer waited a year and a half, the time it takes the sun's light to reach this distance, and then looked again, the nearest stars would have shifted slightly relative to the more distant background stars. This effect, called parallax, is the same one we use on Earth to measure the distances to nearby stars, but it is much more pronounced from out here because the baseline of the observation is so much longer. That is the sky from a few hundred astronomical units. One bright star at the center. Familiar constellations otherwise. A clear, pale band of the galaxy. No atmosphere. No twilight. No haze. Just darkness and the stars, and one fierce yellow point. The planets, of course, are nowhere to be seen. Part 7. The view from a few light years. Now we go further. We leave the Oort cloud entirely. We cross the soft gravitational borderland where the sun's influence fades into the galaxies. We pass through the empty space between solar systems, where the only matter is the thin interstellar medium and the occasional drifting frozen object that may once have belonged to one cloud or another. Let us pause again at 5 light-years from the Sun. We are now slightly farther from home than Alpha Centauri is. We are at a distance that begins to feel galactic rather than planetary. The Sun, from here, is one of perhaps a few hundred stars visible to the naked eye in this region of space. It is not the brightest one. Alpha Centauri A, slightly larger and slightly hotter than the Sun, would actually be brighter from this distance than the Sun itself, if observed from a vantage closer to it. Sirius, dozens of times more luminous than the Sun, would dominate a different part of the sky. But the Sun is still visible, still findable, and still recognizably the color of a yellow main sequence star. Anyone capable of star classification would describe it accurately. They would not, however, single it out from its neighbors. It is one of the more luminous stars in its immediate neighborhood, but it is not extraordinary. It looks, in plain language, like an ordinary star. There is a number that helps make this concrete. Astronomers describe the intrinsic brightness of a star using a quantity called absolute magnitude. Absolute magnitude is defined as how bright a star would appear if it were placed at a standard distance from the observer. Lower numbers mean brighter. Negative numbers mean dramatically brighter. The Sun's absolute magnitude is about 4.83. That places the Sun in roughly the top 10% of stars in the Milky Way by luminosity. By sheer count, the galaxy is dominated by small, dim red dwarfs, stars perhaps 1/10 the mass of the Sun, perhaps 1,000th its luminosity. There may be 300 billion of them scattered through the galaxy, each one too dim to see from Earth without a telescope. Against that backdrop, the Sun is brighter than typical. Against its brighter neighbors, however, the Sun is unremarkable. Sirius A, the brightest star in Earth's night sky, has an absolute magnitude of about 1.4. That makes Sirius A more than 20 times intrinsically brighter than the Sun. Vega, which sits high in the northern summer sky, has an absolute magnitude near 0.6, about 37 times more luminous than the Sun. Alpha Centauri A is slightly brighter than the Sun, slightly larger, and slightly hotter. The Sun is bright enough to be located, ordinary enough to be overlooked. The astronomers of any other civilization within a few light years of us, if they exist, would catalogue our Sun the way our astronomers catalogue theirs. It would receive a label and a few numbers. Spectral class G, 2, V, absolute magnitude 4.83, age roughly 4.5 billion years, distance from them, a small whole number of light years. It would, in their catalogue, be one of thousands. None of the planets, meanwhile, are directly visible. The light reflected by even the largest planet Jupiter is, at this distance, lost in the glare of the central star. Direct imaging of any planet in our solar system from 5 light-years away is far beyond the capabilities of any telescope ever built. The planets, from here, simply do not exist in any visible sense. There are, however, a small number of indirect methods by which a sufficiently advanced civilization could detect our planets. The most powerful of these methods is the same one we use to find planets around other stars. The first is the radial velocity wobble. Every planet in the solar system pulls on the Sun gravitationally, just as the Sun pulls on the planets. The Sun and each planet share a common center of mass called a barycenter, and they orbit that point together. The planet does most of the moving because the planet is much smaller. But the Sun moves too, in a small mirror orbit. Jupiter, the most massive planet, is the dominant pull. Jupiter causes the Sun to wobble at about 40 feet per second. The smaller planets contribute smaller wobbles. A patient enough spectroscopic survey years of repeated, very precise measurements of the Sun's light could pick the Jupiter wobble out of the noise. The Saturn wobble, and the Neptune wobble, and the Uranus wobble would all be there too, harder to find, but in principle measurable. The second is the transit method. If a distant observer happens to lie nearly along the plane of one of our planet's orbits, that planet would periodically pass in front of the Sun from their viewpoint and dim it by a tiny fraction. Earth's transit would dim the Sun by roughly 1/10,000th, a small but detectable signal for a sensitive enough instrument. Jupiter's transit would dim the Sun by about 1%, a much larger signal, easily detected with patient observation. The third is direct imaging with telescopes that have not yet been built. In principle, with vastly larger apertures and clever optical techniques designed to suppress the glare of a central star, an observer could simply see the planet itself. Several serious mission concepts have been studied. None of them have flown. The technology is plausible, but not yet near at hand. The fourth, and arguably the most quietly remarkable, is atmospheric biosignatures. The spectrum of Earth's atmosphere, the particular mixture of oxygen, ozone, methane, water vapor, and other trace gases, is chemically unstable. The presence of free oxygen, in particular, is not the kind of thing one expects on a lifeless world. Oxygen reacts readily with rocks, with metals, with almost everything. For oxygen to persist in an atmosphere for billions of years, something must continually be replenishing it. On Earth, that something is photosynthesis. A future generation of telescopes, perhaps several decades from now, could in principle detect the spectroscopic signature of Earth's atmosphere from 10 or 20 light-years away. The signature, on its own, would not prove the presence of life. But it would be one of the strongest indirect arguments that life of some sort might be present. This is exactly the same toolkit we use ourselves. We have catalogued thousands of planets around other stars. We have not seen most of them directly. We have seen what they do to their stars. From a few light years away, anyone looking back at us would use exactly these methods and would need exactly the same kind of patience that our astronomers need. Years of measurement. Patient extraction of signal from noise. Slow accumulation of evidence. There is no shortcut to finding planets at a distance of light years. There is only patience. Let us add a little more on how planets are detected, because the toolkit deserves a closer look. Radial velocity wobble works because the gravitational interaction between a planet and a star is mutual. When we say a planet orbits a star, we are simplifying slightly. In reality, both the planet and the star orbit their shared center of mass, a point between them, much closer to the star, but not coincident with the star itself. The star moves in a small circle around this point. The planet moves in a much larger circle around the same point. The bigger the planet, the bigger the star's circle. The closer the planet to the star, the faster both circles are completed. When astronomers point a spectroscope at a star, they can measure the star's velocity along the line of sight with extraordinary precision. As the star moves toward the observer in its small orbit, its light is shifted slightly toward the blue end of the spectrum. As it moves away, its light is shifted toward the red. The shift is tiny, far smaller than anything visible to the eye, far smaller than the Doppler shifts familiar from sound, but modern instruments can detect velocity differences of a few meters per second. The sun's wobble due to Jupiter is about 13 meters per second. That is well within the reach of present technology. The sun's wobble due to Earth is about 9 centimeters per second. That is at the very edge of what modern instruments can detect and requires years of patient observation to extract from the noise. A distant civilization with technology comparable to ours could, in principle, measure the wobble of our sun and infer the presence of at least Jupiter. With patience and better instruments, they could detect Saturn. With still more patience and still better instruments, they could detect Neptune. Earth would be far harder. Mercury, Venus, Mars, and Uranus would all be at the edge of detectability or beyond. The transit method works by a different principle. If a planet happens to pass directly between its star and the observer, it briefly blocks a small fraction of the star's light. The amount of dimming is proportional to the area of the planet relative to the area of the star. Jupiter's transit across the Sun would block about 1% of the Sun's light, a deep, easily detected signal. Earth's transit would block about 1/10,000th of the Sun's light, far smaller, but still detectable for an instrument tuned to look for periodic dimming. The catch with the transit method is that it requires the geometry to be right. The observer must lie nearly along the plane of the planet's orbit. From any other angle, the planet does not transit the star at all, and the method fails. This is why the transit method, despite being extraordinarily powerful, only works for a small fraction of nearby star systems, the ones whose planetary planes happen to point toward us. Our solar system, viewed from a random direction, has only a small chance of being aligned for transits. The transit method has one enormous advantage, however. It can detect very small planets if the observing instrument is sensitive enough. The space telescopes we have used in recent decades to find planets around other stars have, by this method, found thousands of planets. Many are quite small. A few are roughly Earth-sized, in roughly Earth-like orbits. A distant civilization with similar technology could, in principle, detect Earth by the transit method, but only if they happened to lie along the right line of sight. They would observe the sun dimming by about 1/10,000th of its brightness once a year, with a transit lasting about 13 hours. That signal, repeated year after year, would tell them that there was a small, Earth-sized planet in roughly the habitable zone of the sun. They would not know what the planet looked like. They would not know whether it had life, but they would know it was there. Atmospheric biosignatures are the third method and the most quietly remarkable. The idea is this: if a planet transits its star, then for the brief duration of the transit, a thin sliver of the planet's atmosphere is backlit by starlight. That starlight, having passed through the planet's atmosphere, carries the spectroscopic fingerprint of the atmospheric composition. With a sensitive enough telescope, one can, in principle, read that fingerprint and infer what the atmosphere is made of. For Earth, the relevant fingerprint would include the strong presence of free oxygen, the strong presence of ozone, a slight presence of methane, the strong presence of water vapor, and the strong presence of nitrogen. The combination, particularly the simultaneous presence of free oxygen and methane, which react chemically and should not coexist for long without continuous replenishment, would be very difficult to explain except by an active biosphere. The biosignature is not proof of life, but it is one of the strongest indirect arguments available. This method requires telescopes that are larger and more sensitive than any yet built. Several next-generation space telescopes are being designed with this purpose in mind. They are not yet operational, but they will be within decades. So that is the toolkit. Patient measurement of wobble. Patient measurement of dimming. Future measurement of atmospheric spectra. With enough patience, any civilization within a few dozen light-years could detect Jupiter and Saturn around our Sun. With more patience, they could detect Earth. With even more patience and the right next-generation instruments, they could perhaps detect a biosignature. None of this is fast. None of this is dramatic. All of it is, in the end, the same kind of patient work that astronomers do every night, every year, every decade. A small but quietly remarkable thing about radial velocity wobble. The technique requires not only that the instrument be sensitive enough, but also that the star itself be stable enough. Stars are not perfectly steady light sources. They have their own internal oscillations, their own surface motions, their own slow brightness variations. These intrinsic stellar wobbles can mimic or mask the wobbles caused by planets. Distinguishing a real planetary signal from stellar noise is, in many cases, the hardest part of the work. The Sun, fortunately for any hypothetical observer studying it from elsewhere, is a fairly quiet star. Its surface oscillations are modest. Its brightness variations are small. Its long-term stability is good. The Sun's wobbles due to its planets should, in principle, be more clearly detectable than the same wobbles around a more active star. This is, in a small way, one of the reasons that life on Earth has been possible for a long time. A more active star one, with frequent large flares, or large brightness variations, or strong stellar winds, would have made Earth's atmosphere harder to maintain, and Earth's biosphere harder to sustain. The Sun's quietness is part of what makes our world the world it is. The same quietness, viewed from outside, would make our planetary system unusually clean to study. A patient civilization watching the Sun could, in principle, extract its planetary structure with relative ease. Part 8. The one thing that is visible. There is one way in which our solar system is not merely a faint yellow star to anyone within 100 light-years or so of us. There is one feature of our presence that we have made ourselves without intending it as a signal, and that is spreading outward into the galaxy at the speed of light. Since the early years of high-power radio broadcasting in the 1920s, Earth has been releasing electromagnetic radiation into space. Radio broadcasts, television signals, military radar, civilian satellite communications, microwave transmissions. The leakage from every broadcast antenna ever pointed near the horizon. The accidental scatter from every dish ever pointed at a satellite. All of it, in addition to whatever it was used for on Earth, escapes into space in every direction, not directly blocked by the planet itself. These signals travel outward at the speed of light. They do not stop. They do not turn around. They do not slow down. They are, after all, electromagnetic waves, and electromagnetic waves do exactly one thing once they have been emitted. They keep going. They do, however, fade. They fade as the square of the distance they have traveled. A signal that was loud and clear at the antenna is, at 1 light-year away, vastly fainter. At 10 light-years away, fainter still by a factor of 100. At 100 light-years away, fainter by a further factor of 10,000. The fading is brutal, and it is unforgiving. But the signal does not vanish. It simply becomes faint. It becomes a quiet murmur where it was once a clear voice. The leading edge of our broadcasts, the oldest signals from the 1920s, has now traveled roughly 100 light-years. Every year, the leading edge moves outward by 1 more light-year in every direction. The newest signals, the broadcasts from this morning, are at the center. The signals from a few years ago are a few light-years out. The signals from a few decades ago are a few decades of light-years out. The oldest are at the outer edge. The volume of space containing our broadcasts forms a sphere centered on Earth. It has a radius of about 100 light-years. The full diameter is about 200 light-years. It is sometimes called the radio bubble or the radio horizon. The bubble is growing. By the time you are watching this, the radius has grown by a few months of light travel already farther than it was when you began watching. Inside this bubble, in principle, is everything we have transmitted. The first commercial radio broadcasts are at the outer edge. Television from the 1940s is slightly inside that. Television from the 1960s is closer in. Modern transmissions are near the center. The contents are not ordered in any meaningful way, but the chronology is preserved. An observer who could intercept and decode the bubble would not only learn that there is a technological civilization here, they would also have, in some sense, an archive of the past 100 years of our broadcast media, preserved in light, expanding outward at the speed of light, drifting through the local stellar neighborhood. There is a quiet beauty in the structure. Every year, the bubble grows by 1 light-year. Every year, a new shell of broadcasts joins the sphere. Every year, the older broadcasts move 1 light-year further from us and out into a region they cannot return from. Civilizations on planets 10 light-years away, if they exist and are listening, would now be hearing broadcasts from the early decades of the 20th century, assuming they have instruments sensitive enough to pick them out of the noise. That last assumption is the catch. The signals are, in fact, very faint by the time they reach any meaningful distance. To detect Earth's radio bubble from, say, 50 light-years away would require a radio telescope considerably more sensitive than anything currently operating on Earth or in orbit. The bubble is not loud. It is not directional. It is not intentional. It is simply there. But it is structured. It is not random noise. It carries the patterns of intelligent encoding. A civilization with the patience and the instruments to pick it out of the background would recognize it as a technological signal. It is one of the small number of physical features of our solar system that can, in principle, be identified as evidence of intelligent life. Almost everything else about us looks like ordinary astrophysics. The sun is one of many. The planets are invisible. The heliosphere and the Oort cloud are invisible. The radio bubble is, in a quiet way, the only thing about us that gives the game away. Whether anyone is listening, we do not know. Whether the signal stands out against the background hum of the galaxy at any practical detection threshold, we do not know. What we know is this: the bubble is there. It is spreading. It has been spreading for 100 years. It will continue to spread for as long as Earth continues to broadcast, and for some time after that. And in the meantime, the bubble is, in the literal sense, the only part of us that has ever left the solar system fast enough to matter. The Voyager probes carry physical messages in case they are ever found. They will take tens of thousands of years to reach the nearest star, and even then their odds of being intercepted are small. The radio signals are already there. For any civilization within 100 light-years of Earth, we have, however quietly, however inadvertently, however faintly, been announcing our presence for the better part of a century. The radio bubble has a structure worth examining more carefully. It is not a uniform sphere of equally bright signals. It is layered, and it is sparse, and it varies enormously in content from one direction to another. The leading edge of the bubble, the oldest signals, the ones that have traveled the longest, is roughly 100 light-years away in every direction. Those signals were emitted in the 1920s. They include some of the first high-power commercial radio broadcasts, the early experiments in over-the-air communication, the radio reports of major news events from that era. They are now the farthest traveled and the faintest part of the bubble. A shell about 90 light-years out contains broadcasts from the 1930s. A shell about 80 light-years out contains broadcasts from the 1940s, including the first widespread television broadcasts in a small number of countries. A shell about 70 light-years out contains the broadcasts of the 1950s, including the first widespread radar systems built during the previous decade, which were among the most powerful artificial radio emitters of their time. Closer in, the bubble grows denser. There are more broadcasters, more frequencies, more transmitters. The shells, corresponding to the past few decades, contain immensely more electromagnetic energy than the early shells. The bubble has thickened over time as broadcasting technology has multiplied. There is also a directional structure. Earth rotates. Earth orbits the sun. The broadcasting antennas on Earth's surface are pointed in particular directions at particular times. The strength of the leaked signal in any given direction depends on which antennas were active and where they were pointed when the signal was emitted. The bubble is therefore not perfectly uniform. It is brighter in some directions than in others. The brightness in any given direction is determined by the cumulative history of human broadcasting along that line. It is also worth noting that the bubble is growing not only outward, but also denser. Each year, additional broadcasts add to it. The signals in any given shell are not the only signals at that distance. New signals are continuously joining the older ones. The bubble is a layered onion of accumulated transmissions. How long will the bubble continue to grow? This is an open question. Modern broadcasting has been moving away from over-the-air transmission for several decades. Television increasingly travels through underground cables and fiber optic networks. Radio increasingly travels through internet streaming. Cellular communications use shorter range, lower power transmitters than the older broadcast antennas. The amount of electromagnetic energy leaking into space from Earth may actually be decreasing. If broadcasting continues to migrate to wired and directional methods, the radio bubble will eventually stop growing in brightness. The leading edge will continue to expand at the speed of light, but the new shells joining the inside will become progressively fainter. The bubble may, in a sense, have a peak brightness, a thickness within which the signals are strongest, and that peak brightness may correspond to the middle of the 20th century, when broadcasting was at its loudest. The peak shell would currently be passing through nearby star systems. As time goes on, the peak shell will move outward, growing fainter as it goes. This is a quiet thing to contemplate. The bubble we have made may not be a permanent or growing feature of our solar system. It may be a transient one, a particular technological era's electromagnetic footprint, expanding outward into the galaxy, peaking in brightness sometime around the turn of the 21st century, and then slowly fading as humanity moves on to other ways of communicating. It also means that any civilization that wishes to detect us by our radio leakage has a window in which to do so. The window is open now. It may, in another century or two, begin to close. The chance that any nearby civilization detects us depends on whether their instruments are sensitive enough, whether they happen to be listening in our direction, and whether they happen to be listening during the window in which we are still loud. The bubble is real. The bubble is spreading. But the bubble may also be a kind of brief candle bright for a century or two, then fading. The thought is humbling. It is also somehow appropriate to the channel's evening tone. There is no urgency to any of this. It will happen at the speed at which it happens. The bubble is, as much as anything else, a slow thing. There is one more soft thing to say about the bubble. The signals within it carry, in addition to their intended content, the rhythms of human civilization. Daily cycles of broadcasting. Weekly cycles. The slow rise of new technologies. The slow displacement of older ones. The pattern of holidays, of news events, of cultural moments, all of it encoded in the times and frequencies of the broadcasts that escaped into space. A civilization with the patience to study our bubble over decades would not only detect us, they would be able to characterize us in ways we ourselves rarely think about. They would notice when broadcasting started. They would notice when television joined radio. They would notice when the broadcast spectrum filled in and grew loud. They would notice, perhaps, when broadcasting began to migrate away from over-the-air transmission and the bubble began to thin. They would see, in some small way, the arc of our technological civilization played back in slow electromagnetic motion. We do not, of course, know whether anyone is doing this. We do not even know whether anyone has the capability. We only know that, if they did, it would be possible. The bubble is real. The patterns are there. The story they tell is, in its small way, the story of us. Part 9. The Solar System, compressed into 3 distances. We have walked outward in stages, from inside the planetary system to a vantage tens of light years away. It is worth pausing now and laying out what the solar system actually looks like at each distance, so that the full sweep can be seen at once. From a few hundred astronomical units, our solar system looks like a single bright star. The sun is fierce, brilliant, and clearly the dominant point of light in the sky. None of the planets are visible to the naked eye. The vast magnetic bubble of the heliosphere is invisible. The vast spherical shell of the Oort cloud is invisible. From this vantage, the solar system is one bright star and a great deal of dark. From a few light years, our solar system looks like a middling yellow star. The sun is no longer the brightest thing in the local sky. It is one of a few hundred visible stars, distinguishable to a trained eye by its color and its absolute magnitude, but unremarkable to any casual observer. The planets are entirely invisible. They can be detected only by careful, patient measurement of how they make the sun wobble, or how they briefly dim the sun when they happen to pass in front of it from a particular viewing angle. The heliosphere is still invisible. The Oort cloud is still invisible. The solar system, from this vantage, is one ordinary star with an invisible planetary system. From tens of light years, our solar system looks like a faint yellow point lost in the haze of the Milky Way. The sun is statistically ordinary. The planets are entirely undetectable to any reasonable telescope. The heliosphere and the Oort cloud remain invisible. There is, however, one thing. There is a slowly expanding sphere of low-power radio emission, about 200 light-years across, growing by a light-year a year, centered on the sun. That sphere is the only feature of our solar system that gives away the presence of intelligent life. Everything else looks like ordinary astrophysics. This is the honest summary. The picture we make for ourselves, the proud little diagram with 8 planets neatly spaced along a single plane, is for our own use. To anyone watching from outside, even from a relatively short distance, the diagram is gone. There is only the star. And, if anyone has the patience and the instruments to listen, the faint, expanding, slowly growing sphere of our broadcasts. A few words on what is missing from this 3-distance picture. We have left the time dimension out. The solar system is not static. It moves. Right now, as you listen, the sun is moving through the local interstellar medium at about 43,000 miles per hour in a particular direction relative to the local stars. Over millions of years, the sun's position relative to the nearest stars changes considerably. The stars we now consider our nearest neighbors were not our nearest neighbors a few million years ago, and they will not be in a few million more. This means that the outside view depends not only on where the observer is, but also on when the observer is looking. A civilization that exists for 10,000 years has a different window of access to us than a civilization that exists for 10 million years. Most civilizations, if they exist at all, may have brief observational windows on us, and we have a similarly brief observational window on them. The galaxy is filled with possible civilizations whose existence is staggered across time. We may share a fraction of our existence with some. We may pass entirely in and out of each other's observational windows without ever knowing. A civilization on a planet around a star 10 light-years away, observing the sun right now, sees the sun as it was 10 years ago. Their telescope picks up the photons emitted 10 years ago. They see 10-years-old Earth. If they begin a transmission to us right now, we will receive it 10 years from now. Round-trip communication, even at the speed of light, takes 20 years for a star 10 light-years away. For a star 50 light-years away, it takes 100. For a star 100 light-years away, it takes 200. The radio bubble is, in a sense, a one-way transmission. We have been transmitting outward for a century. We have not yet been receiving anything in return. If a civilization 50 light-years away began listening 50 years ago, and detected our broadcasts and immediately began transmitting back, their reply would arrive in our radio telescopes around now. As far as we know, no such reply has arrived. Whether that is because no one is there, or because no one is listening, or because no one is interested, or because of some other reason entirely, we do not know. We have also left out the gradual changes in the sun itself. The sun is not a fixed thing. Over its main sequence lifetime, the sun is slowly brightening. It is roughly 1/3 brighter now than it was when it first formed. Over the next 5 billion years, the sun will continue to brighten gradually until it begins to leave the main sequence and become a red giant. At that point, the inner planets will be lost. The outer planets and the Oort cloud will be largely undisturbed. The sun's eventual fate is to shed its outer layers and become a white dwarf, a small, dim, hot remnant slowly cooling for trillions of years. None of these long-term changes affect the 3-distance picture we have built tonight. They simply place it in time. The sun looks the way it does now because we are watching it during a particular stretch of its life, its long, stable, hydrogen-burning middle. From outside, the sun is also, by happy accident, in the most distinctive phase of its life. A G2V main sequence star is a common and recognizable type. Astronomers cataloging the sun from elsewhere would recognize it instantly. That is part of why the 3-distance picture matters. We are watching the sun during a specific window. Anyone watching us from outside is also watching during a specific window. The windows align, when they align, only by chance. Part 10. The Invisible Majority. There is a quiet and almost philosophical point that emerges from the outside view, and it is worth saying clearly. Almost everything that makes our solar system is invisible. By mass, by volume, by sheer extent in space, the solar system is dominated by structures that no eye can perceive and that no telescope at galactic distances can image. The Oort cloud is, by extent, the solar system. The heliosphere is, by physical reach, far larger than the planetary system. Both are invisible from outside. The planets, which dominate our cultural picture of the solar system, are an almost vanishingly small interior detail. They are bright in the sense that they reflect the sun's light efficiently. They are also tiny in the sense that even Jupiter is too small and too dim to be seen from any meaningful distance. The sun itself is the only visible feature of the solar system from far away. And the sun, by galactic standards, is unremarkable. There are billions of stars like it. This is not a sad fact. It is a calming one. The solar system, from outside, is mostly hidden. The hidden parts are not absent. They are simply not visible from where the observers happen to be. The heliosphere is doing exactly what it always does, flowing outward, shaping its long teardrop, deflecting cosmic rays, drawing its slow wake through the galaxy. The Oort cloud is doing exactly what it always does, turning, very slowly, on orbits that take tens or hundreds of thousands of years to complete, releasing one of its members, once in a great while, into the inner solar system. The planets are doing exactly what they always do, moving in their orderly diagram, far too small for anyone outside to see them. All of these things are happening at every moment. None of them announce themselves. There is a soft analog here to the experience of a single life. A great deal of what is real about anyone is not visible from outside. A great deal is hidden by simple distance, by the limits of perception, by the fact that most of what is happening to a person is happening internally. From the outside, a life looks like a faint point of light, with a few measurable parameters around it. From the inside, it is the whole world. Neither view is wrong. They are simply different views, taken from different distances of the same thing. The solar system is the same. From inside, it is everything we know. The Earth, the Moon, the four seasons, the apparent track of the sun across the sky, the bright lights of the planets at twilight, the slow drift of the constellations across a lifetime. All of it is here. All of it is ours. All of it is the world. From outside, none of it is visible. There is only a yellow star and an invisible bubble of charged particles, and an invisible sphere of cold frozen objects, and a faint, slowly expanding sphere of radio noise. Both views are true. Both are real. The solar system is the place you are listening from now. It is also the faint yellow star that another civilization, on another planet, around another small star, within a few dozen light years of us, might be looking at right now without recognizing it as anything in particular. There is something soft and reassuring about the invisibility of most of the solar system, and it is worth letting that idea settle for a while before we move on. We are, from outside, a small bright point. From inside, we are a vast and intricate place. Both pictures are accurate. The vastness from inside is real. It includes the Earth, with all its mountains and oceans and forests. It includes the Moon, with its craters and seas of basalt. It includes the giant planets, with their endless storms and ring systems and dozens of moons each. It includes the asteroid belt and the Kuiper belt, each with hundreds of thousands of named and unnamed bodies. It includes the heliosphere, with its slow flow and its long teardrop tail. It includes the Oort cloud, with its trillion frozen worlds. The smallness from outside is also real. The fact that none of these structures are visible from a few light years away does not make them less real. It only means that the observers at that distance lack the instruments to see them. This is, in a way, the calmest fact about scale. It is not that the small things are unimportant. It is that the importance depends on where you stand. From inside the heliosphere is the difference between a habitable planet and a hostile one. The shielding from galactic cosmic rays that the heliosphere provides is part of what makes Earth's biosphere possible. From inside, the heliosphere matters enormously. From outside, the heliosphere is invisible. The mattering does not change. The visibility does. The same is true of everything we have walked through tonight. The Oort cloud matters, even though it is invisible. The planets matter, even though they are invisible. The asteroids matter. The moons matter. The rings matter. The dust matters. The solar wind matters. The magnetic field matters. The galactic tide matters. All of them matter quietly, in their own ways, in their own scales, and from outside, none of them are visible. The radio bubble is a quiet exception. The radio bubble matters in a way that other features of the solar system do not, because the radio bubble is, in principle, detectable. It is the small, bright accident of our existence. It is the one thing about us that, in the right circumstances, could be picked out from the background. But the radio bubble is also, in a sense, the simplest thing about us. It is a sphere of low-power electromagnetic emission. It carries the patterns of intelligent encoding. It is structured. It is detectable. It is not, however, the deepest thing about us. The deeper things, the conversations we have with each other, the books we write, the meals we share, The long evenings we spend with each other and with ourselves, none of those are detectable from any meaningful distance. They happen from outside, in a place that is invisible to anyone watching. This is true of every life. It is true of every civilization. It is true of every place. The most important things, the most real things, the things that matter most from inside, are largely invisible from outside. They are too small. They are too quiet. They are too internal. The outside view sees only the brightest, simplest, most exposed parts. That is not a tragedy. It is simply the nature of distance. Anyone watching us from outside is doing the best they can with the tools they have. They see what is visible. They miss what is not. The same is true of us when we look at them. We look at distant stars and see only their brightest, simplest, most exposed parts. The lives that may be lived on planets around those stars are, from our distance, invisible. We do the best we can with what is detectable. From outside, we are simple. From inside, we are full. This is, perhaps, the calmest thing one can know about being where we are. There is one more idea worth letting settle. The invisibility of most of the solar system from outside is not unique to us. The same is true of every other solar system in the galaxy. Every star we can see at night, with its own planetary system around it, is mostly invisible to us as well. We can see the star. We cannot see the planets directly. We cannot see the heliosphere of any other star directly. We cannot see the Oort cloud of any other star directly. We see, of every other solar system, only what we see of our own, from outside the central star, and nothing else, and a great deal of inference about what surrounds it. In a quiet sense, this is fair. We are not less visible than our neighbors. They are not more visible than us. The galaxy is full of small, bright knots of warmth, each one surrounded by a vast, invisible structure that nobody on the outside can quite make out. Our place is not unusual in this respect. It is the standard arrangement. So when we look at the night sky, what we are actually seeing is several thousand other solar systems, each one mostly invisible to us, each one with its own planets and bubble and cloud and structure, and each one represented in our sky by a single point of light. The sky is more populated than it looks. It is just that the population is mostly hidden behind the glare of the central stars. We see the brightest, simplest, most exposed parts of our neighbors. They, looking back at us, would see the brightest, simplest, most exposed parts of our system. Everyone is mostly invisible to everyone else. Everyone is, also, mostly there. Part 11. The bubble and the star and the long quiet between. We can hold the outside picture in mind a little longer and let it settle. There is the star. Yellow, middle-aged, middling in brightness, classed as a G2V on the standard astronomical scale, with an absolute magnitude of about 4.83. It is one of perhaps a few 100 billion stars in the galaxy. There are stars brighter than it. There are stars dimmer than it. There are stars older than it. There are stars younger than it. There is nothing about its color, its age, its mass, or its position in the galaxy that distinguishes it from many millions of others. There is the bubble. Invisible, asymmetric, comet-shaped, drawn out into a long teardrop by the solar system's motion through the local interstellar medium. The leading face is rounded and blunt. The trailing tail is long and quiet. The bubble's interior is filled with the slow flow of charged particles from the sun. The bubble's exterior begins where the solar wind no longer has the strength to push back against the interstellar medium. The bubble is so faint that no instrument on Earth has ever directly imaged it. We know its shape only by piecing together what a small number of spacecraft have measured along narrow lines through it. There is the sphere, the vast spherical shell of frozen objects surrounding the planetary system in every direction at once. 1,000,000,000,000 small icy bodies drifting on orbits so slow that they appear functionally motionless. A reservoir of leftover construction material from the formation of the solar system, parked at the gravitational edge of the sun's influence, dark and cold and almost completely invisible. And there is the long quiet between. The space between us and our neighbors is mostly empty. The interstellar medium is thinner than the best vacuum we can make on Earth. The local region of the galaxy is, in any practical sense, dark and quiet. The nearest star is, by ordinary measures of distance, very far away. We are surrounded by an enormous, soft, slow, silent volume of nearly nothing. And we are, ourselves, an almost equally enormous, soft, slow, silent volume of nearly nothing, with a bright yellow point at the center and a thin, spreading sphere of radio noise around us. This is the soft truth about scale. The interesting parts of the universe are tiny. The empty parts are enormous. The interesting parts make the empty parts navigable. The empty parts make the interesting parts beautiful. Without the dark, the lit things would not stand out. Without the lit things, the dark would have nothing to be the absence of. The galaxy is held together by the gentle alternation of the two. We sit inside one of the lit things. We have, for 100 years, been adding a faint glow of our own to the outside of it. From outside, almost no one would notice. From inside, here, in the room where you are listening, the whole arrangement is the only one there is. There is a way to hold all three pictures at once, and it is worth holding them. There is the inside view. The world, the trees and the roads and the rooms, the clouds and the seasons, the faces of the people we know, the sounds of cities and the silence of fields, the feeling of being awake on an ordinary morning, the feeling of being tired at the end of an ordinary day. This is the view we know best. It is the view we use to navigate every waking moment of our lives. It is the view in which the solar system is a single immense place that contains everything we have ever experienced. There is the middle view, the astronaut's view, the view from low orbit, or from a robotic probe near another planet. From this view, Earth is round and small and clearly finite. The clouds are visible as a thin layer over the surface. The atmosphere is visible as a faint blue line at the edge of the planet against the dark of space. The moon is a bright companion at a particular distance. The sun is a fierce nearby light. The other planets are bright points distinguishable from the stars. This view is one that very few humans have had directly. Most of us know it only through photographs. It is the view in which the solar system is a clear, finite arrangement of nearby objects, with everything else far away. There is the outside view, the view we have been building tonight. The view from a few hundred astronomical units, where the solar system is one fierce point. The view from a few light years, where the sun is a middling yellow star. The view from a few tens of light years, where the sun is a faint yellow point indistinguishable from thousands of others, around which a slowly expanding sphere of radio noise is the only signal that there might be anything more here than the usual cycles of stellar evolution. This is the view that no human has ever had. It is the view we can only construct in imagination, by walking outward in stages and then looking back. All three views describe the same place. None of them is more correct than the others. None of them is less correct. They are simply different distances. The inside view captures the texture of life. The middle view captures the structure of the local neighborhood. The outside view captures the position of the solar system within the galaxy. The texture matters. The structure matters. The position matters. None can be replaced by the others. The astronomer who has the outside view, but not the inside view, has missed something important. The poet who has the inside view, but not the outside view, has also missed something. The complete picture requires all three. Tonight, we have been with the outside view. That is the unusual one. That is the one our species rarely takes. It is worth taking, occasionally, because it is calming. It is calming to know that, from outside, we are small. It is calming to know that, from outside, most of what worries us inside is invisible. It is calming to know that, from outside, the solar system is one quiet yellow point in a galaxy of 400 billion others. We do not have to live at the outside distance. Most of us never will. The inside distance is where we live. The inside distance is where the texture is. The inside distance is where the Earth has weather, and where the moon has phases, and where the sun has mornings. But the outside distance is there too. It exists even when we are not using it. It exists when we are sleeping. It exists when we are eating. It exists when we are walking, or driving, or working, or talking. It is, in some quiet way, always available to be reached for, when needed, to put the inside things in perspective. From outside, we are small. From inside, we are full. Both are true at once. Part 12. What the outside view leaves unsaid. There are a few things the outside view leaves out, and they are worth mentioning gently because they restore some of what the view at 100 light-years cannot supply. From outside, our solar system does not look alive. There is no signature of life that can be detected from 10 light-years away with present instruments. The atmospheric spectrum of Earth might, with a future generation of telescopes, betray the presence of an active biosphere. But for now, from outside, our solar system looks empty of life even though, from inside, the place is dense with it. From outside, our solar system does not look thoughtful. The radio bubble carries patterns of intelligent encoding, but the bubble is so faint by the time it reaches another civilization that recognizing it as thought, as opposed to noise, requires extraordinary instruments and extraordinary patience. From outside, we look like a star. From inside, we have spent thousands of years asking what stars are. From outside, our solar system does not look loved. There is no way for anyone watching from far away to know that the small yellow star they have catalogued is, to the small living things on the third rock around it, the source of every warm day, every harvest, every photograph ever taken of a sunrise. From outside, the sun is a number in a catalogue. From inside, it is the daytime. From outside, our solar system does not look like a story. It looks like an entry in an astrophysical database. From inside, it is the only story we have ever known. Every life that has ever been lived has been lived in the inner light of that one star. These things are not contradictions. They are simply differences of perspective. The outside view is true. The inside view is also true. They describe the same arrangement of matter in space, seen from different distances. The outside view is honest about how small we are. The inside view is honest about how complete the place feels from inside it. A great deal of human writing, religious and otherwise, sits in the gap between these two truths. The astronomer's view is one of them. The poet's view is another. Both are looking at the same star. They simply differ on what to call it, and what to think of it, and how to feel about being there. This video, for what it is worth, has stayed with the astronomer's view. The poet's view is yours. A few last things to mention, gently. There is a quiet question that the outside view raises, and it is worth saying it clearly, although the channel will not try to answer it tonight. The question is whether anyone, anywhere, is looking back at us. We do not know. We have looked, in various ways, for signals from other civilizations. We have built radio telescopes and pointed them at nearby stars, listening for patterns that look like deliberate transmissions. We have searched the spectra of nearby planetary systems for chemical signatures that might suggest biospheres. We have inspected interstellar visitors, the very few objects from outside the solar system that have, briefly, passed through our vicinity for any sign that they were not natural. So far, we have found nothing. The galaxy, from our point of view, is silent. There are many possible reasons for the silence. The simplest is that there is no one to hear. Perhaps life is rare. Perhaps intelligent life is rarer still. Perhaps technological civilizations are even rarer than that, and we are simply the only one in our neighborhood. This is, in some sense, the simplest explanation, and it is also one of the most discussed. Other explanations are possible. Perhaps technological civilizations are common but short-lived, and we are alive during a window in which most of them have already ended. Perhaps technological civilizations exist but communicate by means we have not yet learned to detect. Perhaps they are deliberately quiet, for reasons of their own. Perhaps they are deliberately listening but not transmitting. Perhaps the distances are simply too great, and our window of broadcasting is too brief for any meaningful exchange to have happened yet. We do not know. The honest answer is that we do not know. The galaxy could be empty of other intelligent life. The galaxy could be full of other intelligent life that we have not yet detected. The two possibilities are both consistent with what we currently observe. We are, in this respect, at the very beginning of finding out. The serious search for other civilizations has been going on. The galaxy is enormous. The sky is enormous. The search has only barely begun. This video is not the place to settle that question. The channel's purpose is not argument. It is rest. So let us simply note the question gently and set it down. The galaxy is large. We are listening. We have, ourselves, been broadcasting for a century. Whether anyone else is here, with their own bubble of broadcasts spreading outward in their own direction, is something we do not yet know. What we do know is that, if anyone is here, they would see us much the way we would see them. A faint yellow star in a particular part of the sky, with a slowly expanding sphere of low-power radio noise around it. Patient measurement of the star would reveal a planetary system. Patient measurement of the planetary system would, perhaps, reveal a biosphere. Patient listening to the radio noise would, perhaps, reveal patterns of intelligent encoding. None of this is fast. None of this is dramatic. The galaxy does not deliver answers quickly. The galaxy delivers answers, when it does, at the patient pace of light and gravity and observation. From inside, we have 100 years of broadcasting to our name. From outside, that is the beginning of a signal. From outside, the answer to the question, "Are we alone?" is one of the things the galaxy may or may not someday tell us, in its own time, at its own pace, on its own terms. Part 13, the last part, the shape we are. Now, before we close, a few last things to hold in mind, gently and without urgency. We are a sphere, not a disk. The textbook diagram is a flat plate. The actual solar system is a sphere with a small, bright knot of planets at its center, surrounded by a vast bubble of charged particles, and surrounded by a still larger sphere of frozen objects. Almost the entire structure is invisible. We are a faded yellow point, not a special star. The sun is bright enough to be located, ordinary enough to be overlooked. There are billions of stars like it. There are many stars brighter than it. There are many stars dimmer than it. From outside, the sun is a number on a catalogue. From inside, it is the daytime. We are mostly invisible. Almost everything that makes our solar system the size it is by mass, by volume, by reach, is invisible from outside. The planets are tiny. The heliosphere is huge but unseen. The Oort cloud is enormous and unseen. We are mostly dark. We are slowly broadcasting. A sphere of low-power radio noise, about 200 light-years across and growing by a light-year a year, is the only feature of our solar system that gives away the presence of intelligent life. It is faint. It is not directional. It is not intentional. But it is real, and it is spreading. We are part of a galaxy that is full of similar systems. The nearest star system, Alpha Centauri, is similar to ours in many ways, and the next one over is similar in different ways, and the next one over is similar in still other ways. Every star you can see at night is the center of a solar system that, from outside, looks much like ours. Some have planets. Some do not. Some have planetary systems richer than ours. Some have systems poorer. Some are surrounded by their own invisible bubbles and clouds, and we cannot see those either. The galaxy is full of these arrangements. Each one is, from outside, a single bright point. Each one is, from inside, the whole world, for whatever happens to live there. A few more soft things to hold before the closing. We are a sphere, not a disk. We are mostly invisible. We are mostly empty. We are surrounded by a vast bubble of charged particles that no one can see. We are surrounded by a vast sphere of frozen objects that no one can see. We have one bright star at the center and one faint expanding sphere of radio noise spreading outward at the speed of light. The bubble of broadcasts is the only thing about us that is, in principle, detectable from any meaningful distance. Everything else looks like ordinary astrophysics. There are billions of solar systems like this one in our galaxy. There are perhaps hundreds of billions of galaxies in the observable universe. Each of those galaxies contains its own collection of stars, with their own collections of planets, and their own collections of heliospheres and Oort clouds, and slow, long-period comets that fall inward once in a great while. The arrangement we have been describing tonight is not unique to us. It is the default arrangement, the basic pattern, the structure that almost any star like ours has surrounding it. The numbers vary. The shapes vary. The compositions vary. But the basic architecture, bright star, planetary system, magnetic bubble, distant spherical reservoir of frozen objects, is the architecture of most solar systems we have studied. That is, in its own way, comforting. We are not strange. We are typical, The galaxy is full of arrangements, much like ours. The solar system we live in is not a singular accident in an empty universe. It is one example of a very common pattern. It is also worth saying, gently, that this does not diminish what we have. The fact that there are many sunsets in the galaxy does not make any individual sunset less beautiful. The fact that there are many warm afternoons in the galaxy does not make any individual warm afternoon less worth sitting through. The fact that there are many lives in the galaxy does not make any individual life less important to the person living it. The galaxy is full. Each entry in it is, from inside, complete. We have walked outward tonight, in stages, from the planetary disk out through the Kuiper belt, across the heliosphere, through the Oort cloud, out beyond the gravitational edge of the solar system, and then progressively farther to a few light years, to tens of light years. At every distance, the picture has simplified. At every distance, the solar system has looked a little less like the diagram we drew on paper, and a little more like one entry in an enormous catalogue. By the time we reached the outer edge of the radio bubble, the solar system had become a single yellow point, surrounded by a faint sphere of broadcasts set against the long pale band of the Milky Way. That is what we look like, from outside. That is the answer to the question we began with. The diagram does not survive the journey. The textbook image becomes simpler at every step. By the end, only a star and a sphere of radio noise and the dark. And so we leave our own solar system, where we found it a small bright knot of warmth inside an enormous quiet sphere, with a faint and patient sphere of radio noise still spreading outward into the dark on our behalf. From far enough away, it looks like nothing at all. A star and the dark. A point of light and a great deal of empty space around it. From here, where you are listening, it is everything. Let your breathing slow. Let your thoughts settle. Let the day fade away. Sleep well and good night.